This is lesson 3.3, Optimizing with Linear Programming. So what is linear programming? Linear programming is a method for finding the maximum or minimum values of a function over a given system of inequalities, with each inequality representing a constraint. And then the feasible region is the solution set for the system of inequalities, so our shaded region. So we can have two types of feasible regions. The first one's enclosed or bounded by the constraints. So the maximum and minimum of the function will always occur at the vertex. So remember, the vertex is one of the points on the corners of the feasible region. You can also have an unbounded feasible region that's open and can go on forever. Unbounded regions will either have a maximum or a minimum, but not both usually, because it opens and goes on forever in one direction. So let's look at our first example. Graph the system of inequalities. Name the coordinates of the vertices of the feasible region. Find the maximum and minimum values of a function for this region. So our inequalities are 3 is less than or equal to y, which is less than or equal to 6. Y is less than or equal to 3x plus 12. And y is less than or equal to negative 2x plus 6. So only these top 3 are our inequalities. This bottom one is the function that we're trying to minimize or maximize. So that's the one we're going to actually plug numbers into. So our first objection then is to graph our inequalities. So let's get our x and y axis all set up. Alright, so the inequality 3 is less than or equal to y is less than or equal to 6. You could write that as two inequalities if you read from y. Y is greater than or equal to 3 and y is less than or equal to 6. Okay, so we can graph those. They'll both be closed or solid lines. So 3 on the y is here, and so we have a horizontal line. And then we also have one at 6. Okay, so those are those two lines for the first inequality. Then we have to graph the inequality y is less than or equal to 3x plus 12. So remember, we start at our y-intercept of 12, which is all the way up here. And then our slope is 3 over 1. I don't really have room to go up and right, so I'm going to go down and left. And you want to be very accurate with your lines and make sure you go through your whole region. Okay, this one's also a solid line. Okay, and then our last one is y is less than or equal to a negative 2x plus 6. So start at 6, and then it's negative 2x, so down to right 1. Or up 2 and left 1. Oops. And so when you're graphing these, then we have to figure out where we're going to shade. So this is greater than 3 and less than 6, so we're between the two horizontal lines, and then we're less than both the other lines as well. So we're going to shade in this trapezoid region. Okay, and so when it says find the maximum or minimum values, those will happen at one of the vertices. So first step is to write down all the vertices. So we have this first one here. Here's one, third one, and fourth one, which actually is a little off. So hopefully your line's closer to that than mine. So go ahead and write down those vertices. So we have our vertices. Now the one that wasn't on an exact point, the 1.5, 3, if you weren't sure where that should be at, You can always plug that into your equation. Like we know it's 3 because it's on the line y equals 3. So you could plug that in for y and solve for x if you're not sure where that's at. So now that we have our 4 vertices, we have to find the maximum and minimum values. So again, we're substituting them in for the x and the y in this function, 4x minus 2y. So we just substitute those in, negative 3 for x, 3 for y. 4 times negative 3 is negative 12, minus 2 times 3, which is 6. So that would be negative 18. And so we go ahead and we do that for all of these points. And you have to find the maximum min. So I get negative 12 for that one and negative 20 for this one. So the maximum, the biggest number is 0. At the point 1.53. The minimum value, or the smallest, is negative 20 at negative 2.6. Okay, and that's how you use your feasible region to find the maximum and minimum. So the other part of this lesson is to optimize linear functions, which means to seek the best price or amount to minimize cost or maximize your profit. And we often do that with linear programming, the steps we just did. So first thing would be to define your variables. Second step is to write your system of inequalities. Graph them just like we just did, find those coordinates, write the linear function to be maximized or minimized, substitute them in, and select the greatest or least result to answer the problem. So graphing we did in the last problem. Finding the coordinates we did in the last problem. So that's steps 3 and 4. And substituting to get the biggest or smallest we did. The only difference is that you have to write your own inequalities and your own function to be minimized or maximized. So let's look at an example for that. An electronics company produces digital audio players and phones. A sign on the company billboard is shown, so that chart below. If at least 2,000 items must be produced per shift, how many of each type should be made to maximize cost? Minimize cost. So we're trying to minimize cost, so we're going to look for the minimum. The company is experiencing limitations or constraints on production caused by customer demand, shipping, and the productivity of their factory. A system of inequalities can be used to represent these constraints. So if we look here, at least 2,000 items are produced, and then we can use this chart that they gave us below to write our own inequality. So first we need to define our variables. So let's have we have two things. We have audio players and phones. So let's have the audio players be X and the phones be Y. So X and Y. Okay, so the next step is to write a system of inequalities. So it says the audio for the minimum is 600 and the maximum is 1500. So there's two ways you could write that. I like writing it as the audio is between 600 and 1500. If you like writing them separately, you could do X is greater than or equal to 600 and then X is less than or equal to 1500. And then the same for the phone, minimum of 800 and maximum of 1700. Okay, then you could also write it like we did on the other one. Okay, and then we have to look at the 2,000 they gave us. At least 2,000 items are produced per shift. At least means greater than or equal to 2,000. And we have two items produced, audio and phone, and those have to be together greater than or equal to 2,000. So those are the three inequalities that we're going to graph. And we're trying to minimize cost, so we have to write a cost equation for what we're trying to minimize. So if we notice, this here gives us numbers for cost, $55 for each audio and $95 for each phone. Okay, so then we need to graph those and do what we did on the previous problem. So you could go ahead and graph that. This is what that looks like. Okay, so you don't have to take the time to see me do that. And so if I was graphing this though, because there's such big numbers, you'd probably want to go by like 100s or 200s like they did in this picture over here. And then you can do the horizontal and vertical lines for these top two here. And x plus y is greater than or equal to 2,000. So you could get y by itself, but for many of these problems it actually makes more sense to do the x and y intercepts. So remember, to find the x and y intercepts you put 0 into the problem. So if I put 0 in for y, x would be 2,000. So for that bottom equation the x-intercept would be 2,000. And if I put 0 in for x, the y-intercept would also be 2,000. So that's the fastest way to graph that. If you notice on the graph over here, the x and y-intercepts were indeed 2,000. You could have also solved for y and got y is greater than or equal to negative x plus 2,000. And then the slope is down 1 over 1. And since we're going by the same scale of 200 on each side, you can actually go down 1 over 1. So now that we have our graph, we have 5 vertices for our shaded region. So we would have to substitute those in for our cost function to see which one gives us the minimum cost. So we have 600, 1,700. So those are x and y values that we're putting in here. When we put that one in, we end up with 194,500. For 600, 1,400, we end up with 166,000. 1,200, 800, we end up with 142,000. For 1,500 and 800, we end up with 158,500. And the last one, 1,500, 1,700, we end up with 244,000. So again, remember, we're trying to minimize costs. This is how much it costs to make them. So we want the smallest number. Okay, which in this case is the 144 or 42,000. So we want to make on a given shift 1,200 audio and 800 phones, and that would give us the minimum amount for cost.